So when I started to get into computer graphics and I started to learn how to use matrices, multiplying matrices together for rotations and scaling and translations, I knew how to follow the rules. I knew what was going on, don't get me wrong, but I didn't know what it actually meant. What does it mean when you see sine and cosine in a 3x3 rotation matrix and you're multiplying the matrix with a column vector or a vertex? What does it actually mean? What does it actually look like geometrically? Have you even asked yourself the question? There's nothing magic about the matrices themselves. The rules of linear algebra, where we multiply the terms together, apply because of the geometric relationships that exist. So the matrices themselves are not special other than they're a system for storing the values. We know that the x value and the z value are going to change in a rotation type manner. So rather than just simply increasing the x value and the z value and the y value if it was going to be a 3D transformation, whereas with scaling we just increase all of the values equally, it scales the point as we covered in the previous tutorial. This is definitely more complicated and it is definitely more perplexing to get into your head. I put in the title for this video, are you feeling perplexed and it's not painful? It should be perplexing how you get taught at school to follow the rules of matrix multiplication. Then it should definitely feel perplexing when you start looking at something like this, because it just looks really complicated. It adds meaning to what is otherwise just nothing more than a system of rules that we follow, just a memorisation process. But it doesn't really mean anything unless you get practical examples, unless you really start to see the geometry, especially when it comes to computer graphics and things. Obviously sometimes you just need to get on, I understand that, and I often do that. I just need to understand it deeper. I want a more intuitive, deeper understanding. So when you look at the way that the point changes position, clearly you can see there are right-angled triangle relationships consistently throughout the transformation. So if you look at the initial vertex position, or the initial position of the point, and then you look at what happens as it's rotating, new components come into existence, which is the really cool part. So we move one vector such that its tail is at the tip of the other vector. Then when they're joined together in that fashion, we then go from the tail of the first vector to the tip of the next vector. I just can't say it. You're just going to need to look at the animation, I'm sorry. But that's why I did the animation, to make it easier. But the point is that that stays the same. The pink vector is the resulting vector. That simple representation stays the same. Doesn't matter what angle the resulting vector or the point is being rotated to. If you look at what happens as we're rotating, we've got a new vertical component which is created from the x-axis being rotated anti-clockwise, and we've got a new horizontal component which is created due to the vertical axis being rotated anti-clockwise. And so we know the internal angle of the triangles because it's just the angle that we're rotating the point by. From the two right-angled triangles, we can therefore determine those new component values, and they get added on to the changed initial values, and then we get the new resulting x value and z value. So let's start with the first row. We've got cos 30. Let's see where that cos 30 comes into play geometrically on the animation. So the initial horizontal value of 9 multiplied by the cos 30 means that the initial value of 9 is now reduced to 7.83, and that is the adjacent side. So we have got a value of 6. So where does the 6 come from? The 6 is a horizontal component that's come about from the vertical axis being rotated. We know that sine is the opposite over hypotenuse. Also bear in mind that the hypotenuse, the length of the hypotenuse, that initial vector component, the initial value of the point, rotates to become the hypotenuse of the triangles. We now know that the new horizontal component of 6.0 is the opposite side of the new triangle for the vertical axis after rotation. So we've simply got sine 30 multiplied by the initial value of 12. Because we're rotating about the y-axis, the second row doesn't do anything. When you look at the initial blue vector for the z-axis and the initial red vector for the x-axis, as they rotate, their angle between them is still 90 degrees. It'll always be 90 degrees. You can see that it's geometrically correct that the red component of 6 that forms that right angled triangle needs to be added on to the red component of 7.83. So now let's look at the third row and see what values we're adding together there. We add together the initial value of 12, which becomes reduced to 10.44. We add that onto the new component of 4.5 that comes into existence due to rotating the x-axis. Now I've already made some tutorials on linear algebra, so if you want to see an animation that shows you how to rotate around the x-axis first, then the vertical axis, then the interscreen axis. So the first rotation affects the second rotation, and the first and second rotation affect the third rotation. You end up not only getting sine and cosine terms being multiplied together, but you get additional terms coming into existence. So you can always subscribe as well if you want to see more of this kind of stuff. So that's it. I'm gone.